In continuation to my previous class, today I will speak more on steepest descent or ascent method. Now, there are certain properties of this unconstrained programming technique for nonlinear programming. Now, there are few things just I would like to mention in this connection. If I just recapitulate the process once again for you. Now, the process is that there is a function given to us. The function is must be continuous in nature because we are using the gradient technique, gradient of a function at a point. That is why that is very necessary, function has to be continuous. Now, the process tells us that we will start from an initial guess point, that is x naught. Now, in the x naught, once we are guessing that should not be the optimal solution at all for the problem. Now, we will proceed. In which direction shall we proceed? For the maximization problem, we will proceed through the gradient direction from that point, and if it is a minimization problem, we will just proceed to the reverse gradient direction. That is the idea. That is why it has been explained to you that if x naught is the initial point, then we will just find it out what is x1, that is the next point, that is equal to x naught, x1 is equal to x naught plus alpha k. Alpha here we have considered the step length at the kth iteration, and sk is the direction. Sk is positive if it is maximization and it is negative if it is the minimization problem. Now, let us consider one example for this. Now, for example, we are having a function like this. This is the function f(x). Capital X is the vector, it can be in R2 if we consider. Similarly, it can be in R3, that is the surface, etc. If I just consider the simplest case, that is in R2x, then this is a level set of the function. That means f(x) will have certain value at this position. Now, we can have another level set like this, where the functional value would be different, say C1. There can be another level set like this, where the functional value would be C2. Okay. If we consider the initial guess point is here, then if this is my x naught, then if I take the tangent at this point, then this direction is the gradient direction and this direction is the negative gradient direction. Alright. That is why in this point the function will become the gradient direction. Actually, this is not the case, it should be the 90 degree from here, and at this point again it will touch to x2, where after a certain step length, that is alpha naught, again here there will be again we will consider the tangent, again it will move like this. Alright. That is why x naught will move to x1, then x1 will become x naught minus alpha naught, x naught alpha naught, then gradient of f at x is equal to x naught. Alright. x2 will be is equal to x1 minus alpha 1 gradient of f, x is equal to x1. Then we will move to x2. Now, if we consider 3 points x naught, x1, then if we consider x2, what do you see that at this point in the x naught we consider the gradient direction. Again from x1 we are considering the gradient direction. That is why it will just take a zigzag path like this always to reach to the optimal solution at different iteration x naught, x1, x2, x3, x4 like this. Alright. In connection to this, just I will tell you few more things so that we can do steepest descent or ascent method slightly different way, and there are certain properties. First property is that if we just move from x0 to x1, what is our expectation? Since this is the negative gradient direction, then we can say that we have to prove that fx1 must be lesser than fx0. Alright. Similarly, fx2 must be lesser than fx1. This way we will get a sequence in the xkth point, and we will see that fx k plus 1 functional value is much smaller than fx0. Maybe that could be the optimal solution. Alright. For checking the optimal solution, there is a process. Now I will discuss more on that part, but in this connection I will show you few properties. As I said, my initial point is x0. What we are going to prove? We are going to prove that fx k plus 1 is lesser than fxk, where k is the kth iteration and k plus 1 is the next iteration, and this is the minimum of optimization we are considering. That is why if it is x0, x1 would be this way, and fxk plus 1 would be fxk minus alpha k grad of fxk. Alright. If I just expand it in Taylor series, then what we will get here, f of x at point xk, then we will get fxk minus alpha k, then grad of fxk square plus third order term plus fourth order term. That way we can say this is the order of alpha k. We will get several terms, okay, because in the next it would be alpha k square, in the third it would be alpha k cube. Why we are considering alpha k? Because we want to determine alpha k here, and where alpha k is the optimal step length. Okay. Now from here what we see, that you see this is the square term, and the step length is always we are considering the positive step length, because direction we are considering the negative direction for minimization. Unless we consider the step length, that is the length we are considering the positive step length. That is why alpha k is positive, this is positive. That is why we can say from here that fx k plus 1, if we just ignore the other higher order terms, then we can say that fx k plus 1 must be lesser than fx k. What else we can say from here? Just look at the picture. We are moving from x0 to x1, x1 to x2. Now here we can say that these two vectors are orthogonal to each other. Okay, this makes the 90 degree. That is why if we consider the inner product of two vectors, always that will be 0. We can also prove that part. That is why in the next I am going to show you that xk plus 1 minus xk and xk plus 2 minus xk plus 1 orthogonal to each other. If we consider k is equal to here 0, then certainly we can say that x1 minus x2 and x2 minus x1 both are orthogonal to each other. We are going to prove it. Okay. For proving that, what we have to do? We have to consider the inner product of two vectors. What are the vectors? If we just take x1 minus 0 and x2 minus x1, these two vectors we are considering, and we know x1 is equal to x0 plus minus alpha naught grad fx at x is equal to x0. That is why if we can write it minus alpha naught, this difference, and this difference we can write with this way. Alright. Now from here what we see, that this is equal to alpha naught and alpha 1. If we just take outside, then we are getting two vectors, because alpha naught and alpha 1, these are not the vectors, these are the scalars, these are the step length. That is why two vectors, if we can prove that the gradient of these two vectors are perpendicular to each other, rather they are orthogonal to each other, then for in general k we can prove it. Okay, that's why we need to prove that this is equal to 0. Let us see the calculation for it. What we know that d of d alpha k f x k plus 1 is equal to 0 at optimal alpha k, alright, where x k plus 1 is equal to x k minus alpha k, then grad of f x is equal to x k, alright. This is the case. Now, once we are, this is, you see, x is a vector, there are several components for x, we can have n number of components there. That is why if we just use the chain rule here, we are getting that del of f x k plus 1 divided by del of x j is equal to 1 to n into del of x j by del of alpha k, that must be is equal to 0. From here we can say through the chain rule, alright, and this is the necessary condition for optimality of alpha k. Now, from here we can say that grad, this is the grad value, just if we consider this as a vector, then what is this value? This value is nothing but grad of f where x k plus 1, that is why we can write x k minus alpha k grad of f x is equal to x k. This is a vector, and if we just consider that vector as a transpose, and this can be written as del alpha k x k minus alpha k grad of f x k. There is no harm to it, we can write it, this is again a vector altogether, alright. What is this vector? This vector is the direction vector. I can write, let me write it down in the next. Grad of f x k plus 1, if we just consider the transpose of this vector dot grad of f, sorry, x k, this is equal to 0, and this term is nothing but the direction that we are considering as s k. We can consider minus as well, this should be minus of grad f k, that is why this is coming as s k for the minimization problem. Okay, we are getting from here. Okay, then what exactly we are getting? We are getting from here that grad of f x k plus 1, if I consider the inner product, grad of f s k is equal to 0. Clear? Just you put k is equal to 0, then we are getting grad of f x 0, inner product of grad of f x 0 and grad of f x 1 is equal to 0. Am I clear? Okay. I do not think I need to repeat once more this one. Now, from here if we just get this condition, that then we can say that both the vectors are orthogonal to each other, and we can very easily can prove for in general k the same fact. Alright. Now, we will use this concept for this problem. Just after modifying steepest descent method a little bit, I will tell you what is the modification in the next. Now, you see, whenever we are having any nonlinear function, as you have learned in the interpolation method, that any nonlinear function can be approximated by the quadratic function. Okay, Why we are more interested in optimization about the quadratic function? Because quadratic function is of order 2. That's why whatever optimality we will get for that quadratic function, that would be global optimal. That's why if any nonlinear function can be approximated nicely with a quadratic function, and if we find out the optimal value of that quadratic function, then very easily we can say that local optimal is the global optimal. That's why the steepest descent method has been redefined for the quadratic function by employing the concepts I explained to you. What is a quadratic function? Quadratic function is a function of degree 2. Any quadratic function I can just name a one quadratic function like this. Fx is equal to, say, just I showed you before, that's a quadratic function. Just you see, 2x1 square plus 2 x1 x2 plus x2 square plus x1 minus x2. This is a quadratic function of degree of 2 variables and of degree 2, and in general any quadratic function can be written in this fashion, where A is the positive symmetric matrix plus Bx plus C. Here the vector x has been considered as the two-dimensional vector in R2, x1 x2. That's why this function can be written in this form as alpha 1 by 2 x1 x2. If I consider since we have taken half here, that's why the A can be constructed from these 3 components which are of degree 2. x1 square would be 4, because 4 by 2 would be 2, then it will be 2 because I will separate 2x1 x2 into 2 parts. One is the 2x1 x2 plus 2x1 x2 divided by 2. That is why these two terms will come like this, and the third term will be, here it is 1, that is why we will put 2, just double it because of this half, as I said. Okay, and B matrix would be 1 minus 1, x1 x2 plus 0. All right. That's why you see this, if I can write this function in the quadratic form, where this is my A, this is my B, this is my C. All right. This must be x1 x2 transpose. All right. Okay. Yeah, that is transpose. If I consider x1 x2 this way, this is transpose, that's all. All right. And no, this is transpose, and that is it must be x1 x2. All right. Then it is in this form. Now, as I told you that any nonlinear function can be approximated by the quadratic function, that is why we can revisit that thing in this way. I should write not a I should write this as a this way, forget about transpose. All right, then it is okay. Now we have considered x transpose is this one, that much we wanted to say. Now if this is so, let us try to revisit the whole steepest descent method. What are the things we need to find out? We need to find out the gradient direction for this quadratic function, and we need to find out the step length. You will see for quadratic function, finding out the optimal step length, there is a nice process, and that is a function of the gradient of the function at the point xk. That part I am going to show you in the next. just to see, if we consider the function as a fx as a quadratic function, grad of f would be is equal to ax plus b. There is no doubt about it. Therefore, any direction for the minimization problem minus grad f, that is the reverse direction, is equal to minus ax plus b. From here we can say that st x is equal to xi, this is equal to 0. Will you object with it? Because just now, if you remember, we were proving this fact that this fact we proved. What is that? Grad of f, x is equal to, from here, x is equal to xk plus 1, this is the transpose dot sk is equal to 0, alright. Okay. Otherwise, if I just take the transpose of it of the whole case, then we are getting xk dot grad of f t x, no, not t, we are considering the t here, alright. We are taking the transpose of transpose would be the same, is equal to xk plus 1 is equal to 0. We can say it. What is xk? Xk is nothing but s t x is equal to xk. We are considering the separate index here I. That is why from here we can directly say this thing, alright. Once we could say it, you see, again let me just elaborate these calculations for you. SIT, if I write it, SIT is x equal to xi, grad of f at x is equal to xi is equal to 0. It implies that, if you remember just now, we proved grad f is equal to ax plus b, alright. That is why grad of f at x is equal to xi would be, here we are considering I plus 1, it would be axi plus 1 plus b, no problem. That is why here we can say xit axi plus 1 plus b is equal to 0. What else we know? We know that xi plus 1 is equal to xi minus optimal alpha k into grad of f at x is, this is I, sorry, x is equal to xi. We know that. That is why if we just substitute that fact here, then we can write a of xi plus 1 instead of alpha, here it has been considered as lambda, this way there is no harm to it, alright. Here Si is equal to minus grad of f, the same thing, okay. Now if we just readjust it, we are getting this fact, axi plus b together, and this is 1. Then from here we can calculate the value for lambda I or alpha I, whatever you want to say, that is the optimal value of step length in the at the ith iteration, alright. This can be calculated as this way. We can very easily calculate this as this one, just I repeated the same calculations for you, and from here you see we are getting the optimal value of the step length at any iteration is equal to Si to the power t. S is the gradient direction, negative gradient direction for the minimization problem. Transpose of it Si divided by SIT. A is the positive definite matrix, that symmetric matrix I was referring for that quadratic function Si, alright. That is why we need not to formulate the optimization problem I showed you before in the last class to find out the optimal step length. We will simply calculate this formula and we will get the solution of it. Now for this problem, if we just start it from 0, 0, the starting point is 0, 0, then my x0 is equal to 0 0. What is my x1? x1 would be is equal to x0 minus, here we have considered the lambda 0 and s0. What is my s0? s0 is equal to grad f at x is equal to x naught. What is my grad f from here? The function is 2x1 square plus 2x1 x2 this way. That is why the first component of grad f would be the partial derivative of this with respect to x1. That is why it is equal to 4x1 plus 2x1 plus 1, and the another component with respect to x2 we are going to consider 2x2 plus 2x1 plus 2x2 minus 1. This is the grad f at x is equal to 0 0. That is why this value will come as 1 minus 1. Once we could calculate this value, very easily we can calculate the value of lambda 0. What is that? S0 t S0 divided by S0 t a S0. Here S0 is equal to 1 minus 1, 1 minus 1 divided by 1 minus 1, and here 4 2 2 2 we considered for that function, and is equal to again 1 minus 1. If we just calculate the value, you see 2 plus 1 plus 1, that is coming 2 divided by here 4 minus 2, that is 2 minus 2 plus 2 0, 1 minus 1. This is equal to 2 divided by 2 is equal to 1. Therefore, we can say my next x1 would be is equal to 0 0 minus 1 into 1 minus 1. That is why my next x1 is minus 1 0. Clear? This is the calculation for you. Now, this calculation I have done through Excel just to see. X0 is 0 0, minus 1 plus 1, sorry, this is minus 1 plus 1. Now, we have calculated the gradient of first component, gradient of the second component, and everything we have calculated, and the next x1 we are getting minus 1 1, alright, and these are the gradient values for us, gradient of the first term, gradient of the second term. What is the stopping criteria for this whole process, whole iterative process? If we see the respective iterative values of the decision variable, that is x1 x2, rather capital X is very near by, then we will stop. Otherwise, if we see that if the grad f in that point is 0, that means there is no provision for improvement, then we will stop our process. Okay. I have repeated the process one iteration, second iteration, the same process I did for the third iteration, fourth, fifth, and you see the values x7 is coming minus 1 and 1.5, almost 1.5. What did you see? The gradient values are coming almost 0 here. In the previous case also almost 0. Okay. Even if we just repeat the process, we will see the gradient value will come more 0 here. That is why the symptom tells me that you can stop the iteration here. Probably the optimal solution, approximate optimal solution for this problem is minus 1, 1.5. Why did I say 1.5? Because just I approximated the value. Now, you can repeat the process. Now, this process, the calculations, whatever I said to you, that I have done through Excel. What I suggest to you, you repeat the process on your own for the same problem, and just do the same thing for other problems which are supplying to you through our assignment sheets. You do the same process and see how the iteration is going on, how really we are reaching to the optimal solution. And one thing I must mention here, since this method steepest descent method we applied for quadratic function, and due to the very good nature of the quadratic convergence of this quadratic function of this function, we are getting global optimal. That is why we can declare that this is the global optimal value for the given problem. Thank you for today.